Lesson 3.5, Zeros of Polynomials. In this lesson, we'll look at finding zeros of functions, graph them, and then use end behavior and intervals to determine the sketch of the graph. A zero is where the function crosses the x-axis. We've done that plenty of times so far in this semester. To find zeros, you set the equation equal to 0, factor if needed, and then apply the zero product property. That means you simply take each individual portion of the factor and solve separately for the x-intercept or the zero. Example 1a on the right. What are the zeros of f of x equals x times x minus 4 times x plus 3? Graph the function. Well, the first thing we're going to do is find the zeros of the function. To do so, we're going to set the equation equal to 0. So instead of f of x equals, we're going to have x times x minus 4 times x plus 3. And if we set that equal to 0, notice it's already factored. If we apply the zero product property, we're going to set each part set equal to 0 on its own. That outside x, if we set that equal to 0, that is a zero of our polynomial. So that's one answer we'll graph. If we set x minus 4 equal to 0, we'd have to add 4 to move it over, and that means x would equal 4. And that's another 0 for our polynomial on our graph. X plus 3, if we set that equal to 0, we would have to subtract it to move it over, and that means x would equal negative 3. We have 3 unique zeros to this polynomial function. That makes this a cubic function. On the graph, go ahead and plot points at 0, 4, and negative 3. Notice those 3 coordinates are on the x-axis. Then what we're going to do is sketch a graph of the function, and our intervals are going to happen between the zeros. So notice we have an interval from the left-hand side over to negative 3, that first 0 on the graph. We'll call that interval 1. Between negative 3 and 0, that's interval 2. Between 0 and 4, that would be interval 3. And then from 4 on, that would be our fourth interval. So we'll have intervals 1, 2, 3, and 4. Now the rule for the interval is going to be based on the zeros. For example, interval 1, the closest 0 is at negative 3, but it can be anything to the left. So I'm going to say for my interval that x has to be less than negative 3. That's our first interval. I'm going to go ahead and get rid of that purple just so that it doesn't mess with us when we draw our graph in. For our second interval, that's interval 2, the boundaries are negative 3 and 0 for the x-axis. So we would say negative 3 and 0. Pick a number between there. That's our second interval. Our third interval goes from 0 to 4 on the x-axis. And our final interval over on the right-hand side has a boundary of 4 but goes on towards positive infinity. Those are our intervals between the zeros on our graph. So then what we need to do is pick a number. X is less than negative 3. A number that's less than negative 3, I'll plug in negative 4. Between negative 3 and 0, we could pick any number we want. I'll plug in negative 1. Between 0 and 4, pick a number. I'll plug in 2. A number greater than 4 over on that right-hand side of the graph, I'll probably pick 5 for that one. Now, to figure out what happens on the graph, what we're going to do is take the boundaries of those zeros initially. So over here, these 3 boundaries that we have in our factored form, and those are going to go in that top kind of column. We have an x, we have an x minus 4, and an x plus 3. And it says sign, and sign means will it be positive or will it be negative? That's what we're looking for. And we get that by taking the product of our 3 results. Here's what I mean. If we plug in 4 for x, that would be negative 4 for x, that would be a negative number. If we plug in -4 for x minus 4, that would also be negative. And if we plug in -4 plus 3, that would be a negative answer. If you take a negative times a negative times a negative, our product for that first part would be a negative product. Since it's negative, that means the graph is going to go below the x-axis. And then we do the same thing with -1, +2, and -5. Plugging in -1 for x, that's a negative answer. -1 minus 4 would be -5, which is also a negative answer. But now watch this. If we plug in -1 for x plus 3, that would be +2, so that would be a plus for that sign. If you multiply a negative times a positive, your answer would be positive. And that means the graph is going to go above the x-axis. So it'll cross through -3 and go up above. All right, let's try another one. Between 0 and 4, we picked +2. Plugging that in for x, that's a positive output. Plugging that in for x minus 4, 2 minus 4 would be -2. That's a negative output. 2 plus 3 would be +5. If we take a positive times a negative times a positive, we're now back below the x-axis. So the graph is just going up, below, above, below, and so on. It's going to kind of alternate for this pattern. Our last number, +5, if I plug that in for x, that would stay positive. X minus 4, well, 5 minus 4 would stay positive. X plus 3, 5 plus 3 would stay positive, and that means the product is positive. So that means the graph is above. So we said this is a cubic function. There are 3 unique zeros. On that left-hand side, it says it's below. So that means as x goes towards -infinity, the graph is also going towards -infinity. As x goes towards +infinity in our last interval, notice we said the answer was positive or above, so y will go towards that +infinity as well. That means over on that left-hand side, we're going to be down here, and on the right-hand side, we're going to end up above. We have to go through the 3 zeros to get there. So we're going to kind of just approximate where these curves and turning points take us. Over on that left-hand side, I'm just going to pick an area to kind of start, and I'm going to come up through that 0. Now, at some point, it's got to turn and go through 0, drop down somewhere, turn again, and then go up through 4 to go up towards +infinity. That's a very basic sketch of a cubic function that has 3 unique zeros. And we made that interval to kind of approximate where it would be above the graph and where it would be below. Now, we're not exactly sure where that high point is or where that low point is. That's not our focus for this lesson. It's to mainly find those zeros and determine where the end behavior is for the graph. Sometimes when you graph certain polynomial functions, you get zeros that are multiplicities. What that means is it accounts for more than one zero in the equation, but there's only one location for it on the graph. So a multiplicity of a zero is the number of times a zero is represented in a function. And you can have odd or even multiplicities. Anything that's a plain x would default to x to the first power, which technically means it has a multiplicity of 1. But it means it just crosses right through the x-axis like we've normally graphed before. If you have another type of odd multiplicity, x to the third, it will also cross through the x-axis, but it does so at kind of like a slant. It doesn't go straight through it like we'd graph a linear function. It has kind of like a curved path to it as it goes through that 0. Now, even multiplicities are different. An even multiplicity, x squared would be a multiplicity of 2, would be a turning point. So kind of like the vertex for a quadratic function. It would touch the x-axis, but then go in the opposite direction. It wouldn't actually go through to the other side of the graph. And x to the fourth, since that's an even number, that's an even multiplicity, it would have a multiplicity of 4. It will intersect at that 0, and it'll be a turning point, but it doesn't go quite as sharp as a turning point as an x squared does. It kind of flattens out and gets to that turning point and then goes back in the opposite direction. Example 1b. How does a multiple 0 affect a graph or the graph of a polynomial function? Oh, that should be singular, not plural. A polynomial function. So f of x equals x minus 1. That's just a linear function. And your 0, if we set x plus or x minus 1 equal to 0, would just be at x equals 1. So that would have a multiplicity of 1. It's an odd multiplicity. The sketch of the graph, if we graph this line, would just cross the x-axis at plane 1. So go over to 1, and you would just draw your line, whatever it is, and just go straight through it. It doesn't turn, it doesn't do anything unique, it's just kind of right there. If you have x minus 1 squared, that would be quadratic, so that would be a multiplicity of 2. So you'd still set your x minus 1 equal to 0, and you'd get x equals 1. But you'd call that a multiplicity of 2 because it stands for two kind of sets of parentheses. And a multiplicity of 2 means it's a turning point. Now if you kind of sketch a really rough graph of what that would look like, you'd go to 1 and put your point, maybe, there we go. But now that that's a turning point, the graph would go down, touch that point, and go right back up. That's what a multiplicity of 2 would look like on a coordinate system. It's these higher ordered exponents that are unique or new for us. If you have x minus 1 cubed, that means it's a cubic root or a cubic 0 or a multiplicity of 3. Again, because of that x minus 1, the 0 would be x equals 1. And that's a multiplicity of 3. And they'll ask you about multiplicities on your homework. And remember, we said this kind of slants through, so it's not going to be linear like the first example. If we go to 1 and put our point, what ends up happening here is the graph will come up almost like it's linear and then kind of go through it at a slant and continue up. That's a little goofy right there. So it doesn't go straight through it like a linear function would. It makes kind of a unique kind of slant or angle through that 0 of the function. And then x minus 1 to the 4th is even stranger. This has a multiplicity of 4 at 1. 1 is the 0 of the function. So we would say multiplicity of 4. And as you sketch this graph, it's similar to quadratic, so you'd have your turning point at 1, but it's not going to kind of just go straight down and bounce right back up. It kind of does a weird flattening out process. So it'll come down and then kind of flatten out, hit that point, and then go, well, kind of, and then go back up. So it's not quite as distinct as a quadratic is. There's a little bit more of a flattened portion to it. I know, it's kind of weird. We won't do a lot with the multiplicities of 4, but that's the basic shape of what that would look like. Now let's see what graphs will look like when other parts of a function are in the equation. For example, f of x equals x minus 1 times x plus 2. Notice there are two distinct x's, so this is going to be quadratic. Our zeros, if we set x minus 1 equal to 0, would be at x equals 1, and x plus 2 equals 0. That would be at x equals negative 2. So I'd go to negative 2 and put a point on the x-axis, and positive 1 and put a point. Notice they're both multiplicities of 1. They only have technically x to the first power. There's no two or squared or cubed or anything. What that means is this graph is just going to look kind of like your basic quadratic function. It will curve down and then come back up again. So notice the zeros go right through them with a multiplicity of 1. Now watch what happens on the right. We have f of x equals x minus 1 squared times x plus 2. So now we have this x, but it's being squared. So technically that's two x's. This x is just 1 by itself, so this is going to be a cubic function. And cubic functions have arrows that go in opposite directions. Now our zeros, if we have x minus 1, we know that x will equal positive 1, but that has a multiplicity of 2. And that means it's going to be a turning point. For that x plus 2, x will equal negative 2, just like before. We're going to plot our zeros, just like we did last time, at negative 2 and positive 1. Looking at kind of our end behavior, notice both x's are positive. So x squared would be positive, and that plain x on the right is also positive. That means it's going to start on the left-hand side, negative infinity, and end on the right-hand side up at positive infinity. So watch how that happens with only 2 zeros. Since it should start low on the left-hand side, and that a -2 has a multiplicity, sorry, I forgot to write that in, a multiplicity of 1, that means it's going to go right through it. So it's going to go up through -2, and then at some point it's got to turn and come back down. But notice x equals 1 has a multiplicity of 2. That means it's a turning point. So it's going to touch at 1 and then go right back up. So notice it doesn't go through the x-axis, it just has that turning point and ends up towards positive infinity. All right, let's get through these final two. F of x equals x minus 1 cubed times x plus 2. Notice this x is cubed, that means it's cubic. So that means we have a cubic times 1 more. This will end up being a quartic function. So it would be technically x to the 4th if all the x's were multiplied together. For that x minus 1, that's going to be a multiplicity of 3. So it's going to go through it, but kind of at that slant. And then we have our standby x equals -2, and there's our multiplicity of 1. So let's see what this looks like. We'll plot our -2 and plot our positive 1. So it's going to go through our -2, but notice how the x minus 1 is positive and the x plus 2 is positive. Since they're both positive and it's quartic, both the arrows should be up when we're done. And that's kind of following those end behavior rules. So on that left-hand side, it's going to go right through -2. So we just kind of pick a spot and start. And at some point it needs to turn. And we're not totally worried about that yet, but as it comes through and goes through that 1, it's not just going to shoot up through like a parabola. It's going to kind of angle its way through. See, I'm kind of angling it through there. Kind of has a little bit of an arc to it, kind of. Yeah, they're unique, but that should be very basic what that graph would look like. Oh boy, we have one more. Let's get through this last one, you guys. You're doing great, and then we'll call it good for this video. The x minus 1 to the 4th means that this one is going to have a multiplicity of 4, which means it kind of bottoms out through it. Yeah, even crazier. And then that x plus 2, that means x will equal -2, and that has that multiplicity of 1. So we'll plot those, -2, there we go, positive 1. Oh, we didn't name this one. Sorry, I was going so fast. We didn't name this one. If we have that x to the 4th and then this 1 more x, that means this is a quintic function. That was kind of one of the last names that we gave for types of polynomials, if you remember that from the first part of topic 3. To sketch this graph, since it's quintic, that means it's odd. And all of our x's are positive, so that means on the left side, it'll be down low on the output, and on the right side, it'll be up high. To show what that will look like, we're going to go through our -2, that's just your basic multiplicity of 1. And again, we need that turning point somewhere, but instead of kind of being a turning point right at positive 1, it has to sort of bottom out a little. It's hard for me to even draw this in here, so we'll go a little bit lower, so it kind of bottoms out. It doesn't turn like super fast and then makes its way up. So it's similar to a cubic, but flattens out a little bit at that 0 on the right. And these are just really quick sketches of what these types of multiplicities will look like.